Let's talk about how these things take a lot, culminating type thing. Like there's a lot of stuff that goes into this. So we're going to describe how transformers work, what they do, calculate the voltage and current in the primary and secondary coils. Tell your neighbor, tell them why.
And then I realized that was an answer, so now I'm going to say no. I think it's yes. And if it's not, I thought it was yes. Okay. So that
Not
means
worth
I'm
it.
probably wrong.
Not worth it.
You can say anything right now. What if I tell you to be careful?
All right. Correct answer is?
No? Yes?
Correct answer is yes. Okay. There's nothing physically connecting the two. However, there is a magnetic field created by the primary that engulfs the secondary. Okay. So this secondary coil finds itself in the magnetic field produced by the primary. Good with that? Okay. So, this is a good question. I like this question a lot.
And they're completely legal. Just saying. You want to see?
Why did you include the fact that they are legal?
Yeah.
Because, my dad told me that they were illegal one time.
To own one or to?
To own one.
What's illegal?
Oh.
It's not illegal. No. And it's just really cool. We're going to have like 1 million views.
Tell your neighbor, tell them why. If you are note-taking type people, you might review foundational fact number 3.
Other sides are like. Yeah, that makes sense. I don't think it would work when it's studied. Okay, what?
Oh, recognizes connected to a battery.
That really doesn't matter.
That produces direct current.
Oh, so that's
Yeah, I'm sure there. Yeah.
You would spend $750 on me? Wait, how many more weeks of school do we have? And I would not even care about it.
I don't know.
Like that food.
9. Just
Yeah.
Just
Does that count for assignments?
Correct answer is okay. Foundational fact number 3 says if a conductor experiences a changing magnetic field, then voltage is induced. Emphasis on changing. Correct answer is E. We went turn on and off. Okay? So, this initially when it's turned on, so before it's turned on, no magnetic field. Turns on and it's like, boom, magnetic field. There's a change. While this is on, it is producing a magnetic field. It's just not changing. Doesn't count. So, when you turn it off, it's like, yeah, I got a magnetic field. Yeah. Whoa, where'd it go? Changed. Induces a voltage. Okay? Good with that? Okay. Tell your neighbor.
Wait, no. I can see it.
She makes you run down.
Oh, let's see.
Oh, yeah, that was
I don't know what
Correct answer is
D.
D. Dangerous dinosaurs. Okay. Now, this is an animation of how a transformer works. So this kind of puts it all together here. Okay. Lots of concepts, lots of ideas. Okay. This coil here is connected to the power supply. This is going to be our primary. Okay. And this coil is going to be connected to our appliance. This is our secondary. Okay. This gray thing is the iron core. The blue lines are magnetic fields. Okay. Are magnetic field lines. So what we see initially is this. We're going to increase the current through this one, and as we increase the current, there's a voltage induced. But once the current stays steady, we no longer induce a voltage. You no longer get a current out of there. So this is repeating again. We have a steady current, no current coming out there because the magnetic field isn't changing. So how do we deal with that? We have alternating current, which is continually changing, which continually causes this magnetic field to change, which induces a voltage in this conductor because the magnetic field is always changing. This loops of wire are experiencing this change in magnetic field, thus inducing voltage, and it's hooked up to a circuit, which we're saying it is, you get current. Okay, lots of stuff. So you got foundational fact number 1, moving charged particles create a magnetic field. Specifically, you have current going through a wire, creates a magnetic field. That's the blue thing, the blue lines. This coil of wire is in that magnetic field, and if we change the current here, that changes the magnetic field here. This experiences a change in magnetic field, induces a voltage, induces current. Lots of stuff. Kind of the culminating experience. Okay. Tell your neighbor.
That's what I was thinking. So I was like, maybe it's, I mean, who's to say it's possible? It's definitely, I think it's like, that's it's not a whole, like, it's not, yeah. Isn't that the first? Yeah, it's not. I thought it was so bad, I'm like, I right if they literally have it. But like, I just don't.
Correct answer is Buster Brown. Okay. So here, this one's working without anything in it. Okay. There's a magnetic field. You stick like a stick or a log, whatever, that's not going to change that. But if you stick an iron core down here, that's going to strengthen that magnetic field. Okay. Good with that?
Wait, what was the answer?
It will work, just not as well. Buster Brown. Okay. Tell your neighbor. And tell them how you know.
The first one.
This was the only one I got right. But I like so how do you know which one was first and second?
The one that's connected to the power supply is the primary. Correct answer is B, Buster Brown. Okay. So if there are less loops on the secondary compared to the primary, you have a step down. Okay. Thumbs up when you have a guess. Tell your neighbor. Okay. I'm going to go through an example problem. Let's say your primary is 120 volts, okay, coming from an outlet. This has 7 loops. The secondary has 3 loops. So setting up in this ratio, your primary has 120 volts over the voltage of the secondary over 7 loops over 3 loops. See, now we're doing this? Okay. So this ratio here is equal to this ratio here. This has to be less than 120. Does that make sense? So we're decreasing. B, Buster Brown. Okay. Now, to solve for this, you're just going to cross multiply and you get 51.4 volts. And this highlights the idea of why we have a transformer. It transforms the voltage. Okay. Let's say our light bulb couldn't handle 120 volts. It could only handle 50 volts or 55 volts or something. We need to transform or step down that voltage to something that can be used. This is why we have a transformer. Good with that? Okay. The reason why this works, so this is Faraday's law of induction. Okay. Both coils experience the same amount. They have the same cross-sectional area. They have the same rate of change of magnetic field. But the one that has more loops has a greater voltage. The one that has less loops has less voltage. Okay. So the number of loops and the voltage go hand in hand. They're directly related. Okay. So the step down, step up talks about what happens to the voltage. Good with that? Tell your neighbor. Correct answer is A. Good with that? Okay. Current is inversely related to voltage. Tell your neighbor. Okay, correct answer is C. Okay, this is due to conservation of energy. The power in equals power out. Okay. One more time.
Step up, there's more in the secondary.
Yep. Got your neighbor? Correct answer is C. Okay. And correct answer is Buster Brown. Good with that. So whatever happens, the stepping up, stepping down talks about the voltage. Current does the opposite. Okay. Now, if you've ever moved a microwave, you know there's one part that's heavy, one side that's heavier than the other part. That is because of this bad boy. Okay. This is a step up transformer. This is taking it from 120 volts to 600 volts. Okay. This has an iron core around it. It's designed like a figure 8 rather than just a loop. So it's like magnetic fields going this way and this way. Okay. I'm going to pass this around. When you get it, expect about 10 to 15 pounds. Okay. So it's heavy. Good. Okay. So this is a good question. I like this question. It's a little outdated, depending on their phone, but it's still a good question. Have a conversation.
No, yeah, I would have. I would have. You should have. Yeah. If like, don't worry, it's really light. Reach your glasses, like,
Okay. Step up, step down. Step down. We're going from 120 volts out of your outlet to 6 volts. You can find the voltage on your battery of your phone by opening it up and looking at the battery on the fine print somewhere. It'll tell you your voltage. Okay. I wouldn't do like you'd have to restart your phone or power down your phone. You don't have to. It's not like a factory reset, but you got to open it up to find the battery.
Oh, so I have to like
You have to pop the back off. Okay, now it's a battery. So what kind of current comes from a battery? What kind of current comes from a battery? Direct current. What comes out of the outlet? AC.
Is that why phones, like, if they can overheat? Because they have DC?
No. Okay, so I've broken open one of these boxes, and what you get is a transformer, step-down transformer, and up here is a circuit board that converts the AC to DC. Technically, it's called a rectifier. The going from DC to AC is called an inverter. Okay, but so you can pass that around. So any type of adapter, regardless of the color, like the things you plug in your USB ports to, it's one of those. You get it, Maddox? Yeah. You get it? Okay. Oh, sad day. Here's some other. Had a baby transformer. It was like, yes, nice eyes. So transformers come in different sizes. These are the way these are organized is you have your figure 8 iron core, but then the rings, the loops, the primary is wrapped on the inside and the secondary is wrapped on the outside. Okay. It's actually a more efficient design, but, and then here's an itty bitty one. Okay. Other examples of transformers are in your car. So your car is a 12-volt battery. But in order to, like your spark plugs in your car, to generate a spark, that requires like 10,000 volts or something. There needs to be a huge step up transformer. This is the induction coils. Okay. All right. So this question usually leads to the follow-up question like, what about wireless charging? You now know enough physics to be able to at least like digest this. So in the charging base, there is a coil of wire with alternating current, creating a changing magnetic field. There's a coil of wire in your phones that have this wireless charging capability that is inside, when it's near it, it's inside this changing magnetic field, which induces an alternating current. And inside here, you'll have a microchip that will convert that to DC and charge your battery. Does that make sense? Okay, so here are the literal coils of wire. Alex. Same way. Same way. They just have a smaller coil. Yep. So there's a couple different ways of charging. Induction is called inductive charging. That's what we just talked about here. And then there's magnetic resonant charging, kind of the same way, where this base can charge devices around it because it's in the magnetic field. Charging with a wire is way more efficient, faster, because you don't have, like, it's not going through, the magnetic field's not going through the air. It's just, but it's still really cool, the fact that you don't have to plug anything in. It's just kind of just charges. Okay. Another application of induction is the stoplights that like sense that you're there. There's I don't know if you ever noticed, but in the asphalt they've cut, it looks like an octagon. They've shoved a loop of wire, a big loop of wire that's probably like 3 feet in diameter underneath the road, and when there's current going through it, and then when you roll over that, that changes the magnetic field and it registers that. And so so that's another application. Okay. So a main application talks about this. Tell your neighbor the answer to both of these questions. Correct answer is, okay, we want a low current, which requires a step-up transformer. Everybody good with that? Okay. So, I don't know if you are aware, well, I guess I don't. I don't know where the power company is that creates our electricity for Lafayette, but the power company that creates electricity for Indianapolis is south of Bloomington. We transport electricity miles and miles and miles going through wires. There's lots of resistance, lots of energy wasted to get it from the power plant to where we're using it. So to reduce how much is being wasted, we need a lower current. So the solution, or one solution, the solution that we're using is this idea of using a step-up transformer. Okay, we're going to take it, create the electricity in the power plant, and then we're going to step it up to high voltage, but it's going to be a low current. Okay, so this is why we have high voltage power lines. Okay, some power lines have high enough voltage I can actually hear the electrons, like the hum. Like remember when I plugged the speaker into the AC and you hear the boom and you could feel the speaker? I've been under power lines that you can hear that buzzing with 60 hertz cycles a second. Okay, so they use that to transport the electricity across the state, and then they'll go through a step down transformer before it's used. Okay, and this is I don't know if you ever heard in history the electrical wars between Thomas Edison, he was DC, and Nikola Tesla, which was AC. This was the clincher for AC. The fact that we can transport this electricity across the state, across large distances with this step up and step down transformer. Okay. So here's a little more, this was pretty simplistic. This is a little more realistic. So we step it up. Some industries actually tap into this high voltage power just for their machinery. Step down, I'm making this up, to like a couple thousand volts. Other companies use that. And then we step it down yet again before we use it in residential. Okay. So this substation, this is one of these. This one's off of Lindbergh by the celery bog. Top sit right here. Okay. These are like your forbidden electrical jungle gyms that you always wanted to play on, but surrounded with barbed wire and a lot of danger, death signs. So this is taking high voltage, like tens of thousands of volts, and stepping it down to a couple thousand volts. And then these things here, we're kind of getting away from these, but these are like the trash can looking things on telephone poles. These are things that squirrels like to chew on and blows up and knocks out a whole city block. Okay. If you're sitting in these two rows, you can see out the window. There's two of them sitting on the telephone pole right above that boom truck. Okay. This is taking it from a couple thousand volts down to 120 volts. Okay. Cool. That we are burying these as time goes on. We're putting these on the ground because it's a pain to deal with squirrels. And evidently moles don't like to chew on them. I don't know. Okay. Cool with that? Ben. Yes. Yep. So the ones that are going, they're putting them in the ground. They've got those green plastic utility boxes. Like, don't open this. Okay. So now you know kind of the whole story of how electricity is generated and transported to your house. That's the physics show today, kids. Got a worksheet due tomorrow.